So in second year, first lesson is the waves. In this one waves, the concept name is vibration modes. Vibration modes in stretched string. Stretched string. Vibration modes in stretched string. So how to find that one? Vibration modes in a stretched string. We will find out that one by using the stretched string. As well as we can find it the frequencies. We can find it that one frequencies in a stretched string by using the 1 loop, 2 loops and 3 loops and number of loops. So now here it is. Now I am taking the one stretched wire with rigid support. Now this one rigid support and one straight wire and fixed with elbow of the rigid support. This is that stable, means rest position of the wire. So this rest position of the wire is like this one mean position because I am taking one stationary wave with x direction. X direction. So now this is on 0, means from this one origin point, this is one mean point. Mean point means 0 position, like this one rest point of the stretched wire. In a plucking wire, one time that one wire, we can get waves. So that way is first traveling towards the rigid support and forming the waves in the form of transverses and collision with the rigid support. When it collision the rigid support, then it will be reflect. It will be reflect and moving in a opposite direction, and it will be form the stationary waves. These are the stationary waves. So it will be formed after reflecting the wave. Then here it is. We need to form two definitions. What are the nodes and antinodes? Nodes and antinodes. Nodes and antinodes. So what is the node? In a stationary wave, the zero displacement of the particle. The zero displacement of the particle in a stationary wave, you call that one nodes. Nodes means zero displacement. Zero displacement. So this is zero displacement of the particle in a stationary wave. That points we are calling nodes. Means these points is totally nodes. So nodes just we can represent with the symbol n, like that one nodes. N. Means for example, if we selecting these like the stationary waves, how many number of nodes? 1, 2, 3, 4, 5. And 6. Because these are the zero displacement of the particle in a stationary wave. And antinodes means the maximum displacement of the point. Maximum displacement of the point. Maximum displacement of the point in a stationary wave, we have called that one antinodes. Means these are the maximum displacement. Means the antinodes, just you can take it upward or downward only. Upward as you wish, upward or downward. So now I am taking upward. So upward, where is the maximum points? 1, 2, 3, 4, 5. Means 5 antinodes. So antinode, AN, means just we can represent it with AN, and AN. So we can find it is like nodes and antinodes. Based on nodes and antinodes. We can find it. Length of the wire or wavelength of the stationary waves. And we can find it based on, by using the wavelength, we can find it the vibrations. Like number of vibrations means frequency. So based on wavelength, we can find it the frequency also. So now here this, if you observe, already you know the wavelength. Wavelength means the successive distance between two successive crests. The distance between two successive crests or two successive trough. That distance we are calling wavelength. So just once again, I will draw the diagram by using that one wavelength, and I will find it that wavelength between the nodes and antinodes and nodes and nodes. Now I am taking one stationary wave is like. Just I am taking only one wavelength line. So according to definition of the wavelength based on crest and trough. So means now here it is I am taking according to definition of crest and trough, the distance between two successive crests. That's we are calling wavelength. So the distance between crest means crest is that one upward. Upward is maximum distance point we are calling antinode. So this is what antinode. So the distance between two successive antinodes that we are calling also equal to wavelength. Wavelength means lambda. Means the distance between antinode to antinode equal to lambda. As well as this is the distance between node and another node. Node and node is equal to lambda by 2. Node and node is equal to lambda by 2. So as well as here this, the distance between node and antinode is equal to lambda by 2. So once again this, here it is, the distance between antinode to antinode is equal to lambda, and the distance between node to node is lambda by 2, and the distance between antinode to node is lambda by 2. So based on these distances we can find it the number of vibrations, like that of frequencies. So now here it is, now I am taking one stretched string wire forming with stationary waves. So now I am taking one stretching wire with number of loops. This like with the number of loops I am taking. So now I am taking this like. So this stationary wave moving with velocity v and wavelength lambda and frequency mu. Any one wave is moving with velocity v and wavelength lambda and number of frequencies. Now here it is, the general relation between this v lambda mu means the relation between wave velocity and wavelength and frequency. That relation v is equal to mu lambda. So here it is, the wave velocity in a stretched string. How to define the one? Here it is, first I need frequency. So frequency mu is equal to v by lambda. So just I changing the relation. Then here it is, v is equal to under root t by m. Why I am writing this one t by m? Because here it is wave velocity in a stretched string. This is a solid material. So we can find the wave velocity v is equal to under root t by m. So here it is, t is equal to tension, and m is the linear density. So by using this, then finally mu is equal to, from this one equation, v value under root t by m and by lambda. Means finally we can write once again, mu is equal to 1 by lambda into under root t by m. This is that equation. So general equation, frequency in a stretched string. The equation of frequency in a stretched string, mu is equal to 1 by lambda into under root t by m. This is the general equation in a stretched string wire. Now I am using this, mu is equal to 1 by lambda into under root t by m stretched string frequency equation. Now I am selecting only one loop. In one loop, what is the frequency equation? Now first one is one loop. When a stationary wave in the form of one loop, with the formation of two nodes with the one antinode. When a stationary wave forming with one loop with the two nodes and one antinode, then the length of the stretched wire L is equal to lambda by 2. Why lambda by 2? The distance between two nodes is equal to lambda by 2. So when a stationary wave forming with the two nodes with one antinode, then the length of the stretched wire L is equal to lambda by 2. So now I am taking this, L is equal to lambda by then lambda is equal to 2l. So from the general equation, mu is equal to 1 by lambda into under root d by l. So lambda value is there. So now I am taking, this is the only one loop. So first loop. So this first loop of frequency I am taking mu naught. Mu naught is equal to 1 by lambda means 2l into under root d by l. So this equation mu naught is equal to 1 by 2l into under root d by l. So this equation is that one loop of the frequency of a stretched string wire. So here it is. This mu naught is for the first harmonic. First harmonic or fundamental frequency. Mu naught is that one. First harmonic or fundamental frequency. Fundamental frequency. So this is the first one. And one loop completed. And next one, two loops. When a stretched string forming the stationary waves with the two loops, what happened? What is the frequency equation? So now I am taking two loops in a stretched string. Second one, two loops. So now I am taking two loops. So two loops, 1 and 2. Two loops. When a stationary wave forming two loops, how many nodes is there? 1, 2, 3, and anti-nodes how many? 1 and 2, an and an. Now in the stretched string, when a stationary wave is forming with the 3 nodes and 2 antinodes, then length of the stretched string, this is the lambda by 2 and this is the lambda. So total length of the stretched string L is equal to lambda by 2 lambda by 2. So when a stationary wave forming with the 3 antinodes, 3 nodes and 2 antinodes, at that time the length of the stretched string L is equal to 2 lambda by 2. So now I am writing this there. Nodes, number of nodes is equal to 3 and antinodes is equal to 2. Then length of the stretched string L is equal to 2 lambda by 2. 2 lambda by 2. Now I need from that one first equation. What is the general equation? From general equation. What is the general equation? Mu is equal to 1 by lambda into under root d by l. Now lambda value is there. L is equal to 2 lambda by 2. So lambda is equal to 2l by 2. So now I am substituting this lambda value in this one general equation. So in a first loop I am taking mu naught. In a two loops now I am taking frequency mu 1. So mu 1 is equal to 1 by lambda value 2l by 2 to l by 2. So under root d by m. Now these are denominators that changes. So denominator is also numerator with the denominator and the other one. So now I am changing that. So the values it will be changes. Mu 1 is equal to 2 by 2l under root d by m. This equation I am changing this line. Mu 1 is equal to 2 of 1 by 2l into under root d by m. Now mu 1 is equal to 2 into 1 by 2l of under root d by m is equal to mu naught. Mu naught is equal to 1 by 2l into under root d by m. So that's 1 by 2l into under root d by m. Now I am substituting this mu naught means 2 mu naught means second means 2 loops of the frequency mu 1 is equal to 2 times of the fundamental frequency. Means in this one 2 loops, in this one when you selected 2 loops, the 2 loops of the frequency, means number of migrations modes is 2 times of the fundamental frequency, means is the in my first loop. So this one. So here it is. Mu 1 is equal to first overtone or second harmonic. First overtone or second harmonic. So this one 2 loops. We need 3 loops. Third one, 3 loops. 3 loops. When 3 loops is selected, now I am taking 3 loops. 3 loops I am taking. So if you selected 3 loops, 1, 2, 3, 4 means 4 nodes. And 1, 2, 3. 3 antinodes. 4 nodes and 3 antinodes. So now here it is. If you selected when a station waves formed with 4 nodes and 3 antinodes, then length of the structure string. This is the lambda by 2. This is the lambda by 2. This is the lambda. So total length L is equal to 3 lambda by 2. Then lambda value is equal to 2L by 3. 2L by 3. From the general equation. Now I am taking 3 loops. So now I am taking mu2. The frequency of 3 loops is mu2 and 10. Just otherwise I am following. So mu2 is equal to 1 by lambda value 2L by 3 into under root A by M. Under root A by M. Now here it is. mu2 is equal to 3 of 1 by 2L into under root A by M. Means mu2 is equal to 3 mu naught. Means in 3 loops, the frequency of a 3 loops in a structure string when you form the station waves, that is equal to the 3 times of a fundamental frequency. 3 times of a fundamental frequency. Now here it is. mu2 we are calling second harmonic or second harmonic or second overtone or third harmonic. Second overtone or third harmonic. Just we can find it easily. Left side number we can call that one overtone, and right side number, the multiple integral number, we can call that one. Third one means harmonic. Right side multiple number is harmonic. Left side suffix number of the frequency, you can call that one overtone. So in this one 3 loops, second overtone or third harmonic. Now finally what? Now finally the ratio of the frequencies in a structured string in the order wise. Mu naught is to mu1 is to mu2 is to mu3 is to dash dash mu n minus 1 is equal to 1 is to 2 is to 3 is to dash dash up to n. So this is the number of vibration modes in a structured string one. Now once again I will explain everything shortly. So number of vibrations in a structured string. So from that one structured string, if you are structured string with a number of loops, from that one all loops I am selecting first loop only with one loop. When a stationary wave is forming with the 2 nodes 1 antinode, 2 nodes 1 antinode, at that time the length of the stationary wave L is equal to lambda by 2. So from that one L is equal to lambda by 2 with the one loop, then lambda is equal to 2L. So the frequency general equation in the structured string, mu is equal to 1 by lambda into under root 3 pi. So then lambda value is 2. This lambda value I am substituting 2L. So mu naught is equal to 1 by 2L into under root 3 pi M. So here it is. In first loop, the mu naught I am calling that, you are calling that mu naught is first harmonic or fundamental frequency. First harmonic or fundamental frequency. Means here it is 1 by 2L into under root 2 by M means into 1. If there is no any one with 1 means 1 means. So first harmonic or fundamental frequency. Then now I am taking 2 loops. When a stationary wave in a structured string forming with the 2 loops with that one 1, 2, 3 nodes and 2 antinodes. Then the length of the structured string. This is a node lambda by 2, node lambda by 2. So totally length of the structured string L is equal to 2 lambda by 2. Means the length of the structured string 2 lambda by 2 when 2 loops if is selected. values changes if you going to the numerator. So then this one mu1 in that second, like that one second harmonic in a second loop. That one mu1 is equal to 1 by 2 L by 2. Then finally mu1 is equal to 2 by 2 L under root T by U. So this equation just I am changing generally. So mu1 is equal to 2 of 1 by 2 L under root T by U. So now if this 1 by 2 L into under root 2 by T by M is equal to the fundamental frequency. Now I am writing that 2 into this total value is equal to the mu1. So mu1 is equal to 2 into mu0. So mu1 we are calling first overtone. mu1 is called as the first overtone. Here is the second, we are calling second harmonic. Means right side multiple numbers giving the harmonic number and left side suffix number giving the overtone number. And next one, 3 loops. If we selected 3 loops, 2 loops considered and 3 loops continuation I am calling. So 3 loops. When a stationary waves forming with the 3 loops at that time, how many notes are there? 1, 2, 3, 4. 4 notes. And 1, 2, 3. 3 antinodes. When a stationary waves forming with 4 notes and 3 antinodes, then the length of this stretching string L is equal to 3 lambda by 2. L is equal to 3 lambda by 2. Here it is. When L is equal to 3 lambda by 2, then lambda is equal to 2L by 3. Lambda is equal to 2L by 3. From this one equation, already we have the general equation. Mu is equal to 1 by lambda into under root T by M. So now I am selecting 3 loops. So just I am following your otherwise mu1 after that mu2. So is this one second overtone. That's one I represented with the mu2. So mu2 is equal to 1 by lambda replace 2L by 3. Now I am writing 2L by 3 under root T by M. Now we get this denominator changes. Mu is equal to 3 of 1 by 2L into under root T by M. 1 by 2L into under root T by M is equal to mu0. So mu2 is equal to third means 3 into mu0. So here it is mu2 is equal to mu2 is called second overtone. Second overtone. Just simple. Left side overtone, right side harmonics. So mu2 is equal to means here the second overtone or another like third harmonic. These are the, if your continuation is this like, how to get that one ratios, vibration modes, like the frequencies ratios in a stretched string, how to get that one mu0 ratio with a mu1 ratio, mu2 ratio, mu3 ratio, that is up to n minus 1 is equal to 1:2, 2:3, 3:, up to n we can get. This is the vibration modes or frequencies ratios in a stretched string. If you follow through the number of loops, we can get the ratios. These like 1:2, 2:3, up to this one. And next one, after compare this, based on this equation, what are the losses? The loss of the stretched string. The loss in a stretched string. Wave losses in a stretched string. How many losses is there? How to find that one? We will discuss that. How to look at it. So here it is. So now loss in waves. Loss of waves in stretched string. So the general equation in a stretched string, the frequency mu is equal to 1 by 2L into under root T by M. Under root T by M. Here it is. How many losses is there? 3 losses is there. First, length law. Length variations perfectly it will be changes the length when we selecting the different lengths like that one notes. So length law. If you selected or if you discussing about that one length with respect the frequency at that time, the linear density and the tension is constant. When tension and linear density constant at that time, the frequency is inversely proportional to the length of the stretched string. So once again, length law in a structure string. So if we are discussing about that one, length law, remaining all constant except the frequency and the length. So now here it is, when in structure string, for example, if you selected one structure string with constant values, with constant tension and linear density, at that time, the frequency of a structure string is inversely proportional to the length of the structure string. Means when a frequency is increasing, then length is decreasing. Just simple. For example, I am selecting just 5 centimeters of structure string, and second one I am selecting 10 centimeters of structure string. So now here it is. If you flag that with the same applying forces on first one, second one. Here it is. Distance is very less with 5 centimeters. So number of vibrations is coming nearly. Number of vibrations means length lesser but vibrations more. Same force applied when on that one 10 centimeters, it will be giving the more distances, the vibrations it will be formed. Means the distance is more between vibration to vibration. So when a length is increasing, the frequency is decreasing. So that's like the length law in structure string is also the frequency is inversely proportional to length of the structure string when the linear density and the tension constant. And second one, tension law. If you discuss the relation between tension and frequency of a structure string, now remaining all constant. Like this, when a length of the structure string and linear density are constant. Now, what happened? The frequency in a structure string is directly proportional to square root of the tension of a structure string. This is the first one. This is the second one. When the structure string of the length and the linear density when a constant, at that time the frequency is directly proportional to the square root of the tension. That's frequency is directly proportional to tension under root T. So this is one second. And the third law is the last one. Linear density law. From this one linear density law, so if you discuss the relation between linear density and frequency. Now, at that time, tension of the wire and length of the wire are constant. When a tension of the wire and length of the wire constant, at that time, the frequencies in a structure string is inversely proportional to square root of the linear density. When tension and length of the wire is constant, at that time the frequency in a wire is inversely proportional to square root of the linear density. This is the three laws. So 3 losses. We have taken 3 losses in a structure string in the form of waves. So just simply we can do that one. From this one equation we can explain that. Just about that one, length law means just closing this one because these two quantities are constant. So if you close this one, it's constant. There is no changes. So what looks like mu is equal to 1 by L, 1 by 2L. Just we discuss it. This is a multiple number. Leave it about it. 1 by L means inversely proportional. And now if we discuss the tension law, means remaining M and L constant. Just close it that one. Doesn't changes. That are two quantities. So what would look like? This is a square root T. Means mu is equal to square root T. Means directly proportional to square root T. And if we discuss with that one linear density and frequency remaining constant, means length and tension constant. Just close it that one. Doesn't changes. So how to look like? 1 by square root L means mu is inversely proportional to 1 by M. This is the loss of waves in a structured string. So this is the first concept is the number of modes or frequencies in a structured string. How to ratio that one? Mu naught is to mu 1 is to mu 2 is to mu of n minus 1 is equal to 1 is to 2 is to 3 is to up to that one n. And the loss of waves in a structured string, that's we can get that one. Mu is directly proportional to 1 by L and mu is directly proportional to square root T inversely proportional to 1 by n. Means the frequency is inversely proportional to the length of the structure string, and frequency is directly proportional to the square root of the tension, and frequency is inversely proportional to the linear density, square root of the linear density. These are the laws of states in structured string. Then after, open organ parts and closed organ parts. First, what is the open organ parts? What is the closed organ parts? Open organ parts and closed organ pipes. Open organ pipes and closed organ pipes. Open organ pipes means the pipe of the one end is both of ends. This is for example one is pipe. So this pipe of the two ends when you open like this one. For example, one tube like that one pipe, like that one tap pipe. So that tap pipe both of end. So one end we can insert into the water can tap, and another end the water will be come from the another end. So that's right. So these both ends are open. When one pipe is totally both ends are open, that pipe is called as open organ pipe. Open organ pipe. As well as when a pipe of the one end is closed, and one end is open. This is the closed end and this is the open end. If you see that one, when one pipe of the one end is closed and one end is open, that organ pipe we are calling closed organ pipe. Closed organ pipe. So this is the open organ pipe. This is the closed organ pipe. In open organ pipe, both ends are opening, and in closed organ pipes, one end is open and one end is closed. So this is about that one, open organ pipes and closed organ pipes. Then after, how to forming the vibration modes in open organ pipes and in closed organ pipes, we will discuss by using that end of that one, by using the different nodes and different antinodes with different nodes with different antinodes. How to get that one? Ratios of the frequencies in your open organ pipe. We will discuss now. Now we are going discussing about that one, vibration modes and ratios of the frequencies in a open organ pipe. Now I am selecting open organ pipe. In open organ pipes also, if you are selecting like that one stationary waves, like that one, is there any wave traveling through the one pipe? When a collision with the, or when a two or more when you are moving in the same direction or opposite direction, at any one time or at any instant time, stationary waves it will be formed. When a stationary wave forming with the different nodes and the different antinodes, what happen? What are the modes and what is the frequencies ratios? We will discuss now. Now I am taking open organ pipes means vibration modes in open organ pipes. Open organ pipe. So from this one, open organ pipe. Already now, open organ pipe means both ends of the pipe it will be opened. When both ends are opening, that pipe we are calling open organ pipe. Now in open organ pipe, already know the general equation. For example, now I am selecting one open organ pipe. This is the open organ pipe. These are both ends are opening. Now you can take it this one ends open, totally both are open. Now we have this. When a stationary wave moving with the velocity v and wavelength lambda and frequency mu. The general formula between this relation v lambda mu, v is equal to mu lambda and mu is equal to v by lambda. This is a general equation in a open organ pipe. In a stretching, we can write that one v is equal to t by m because that is one linear density, because that one is solid substance. Here it is open organ pipe is gas. The air, the sound or anything like it is traveling through the air molecules, through this one organ pipe. So at that time we can find that one wave velocity easy. So now from this one, now I am selecting first case. In first case, now I am taking this line. Just a bit without that one, I will draw the neatly. This like I am making. So in first case, I am taking this line. So now if you observe here, this is the antinode part, this is the antinode part, this is the node part. Means if you observe in this one, what happened here is the both ends are opening, open other part. In this one and two antinodes, one node. Means one node and two antinodes. Then length of the air curve, how to find that one? I need total length. L is equal. So now already I said the distance between node and antinode is equal to lambda by 4, and this one is also lambda by 4. Means lambda by 4 plus lambda by 4. Lambda by 4 plus lambda by 4 is equal to lambda by 2. Means many stationary waves forming with two antinodes with the one antinode. Then air column length. Then length of the air column is equal to lambda by 2. Means L is equal to lambda by 2. Then frequency in a first air column, that's I am taking mu naught. Mu naught is equal to V by lambda value. How to find it? L is equal to lambda by 2. Then lambda is equal to 2L. So lambda value I am taking 2L. So this is the first equation in this one. So when in open organ pipe, the station waves forming with the two antinodes, one node, then length of the air column is lambda by 2, then lambda value is 2L. Then frequency, the fundamental frequency in a open organ pipe, mu naught is equal to V by 2L. So this frequency we can call fundamental frequency. Or another line. Here in this, there is no one way. So that one is also we call that one first harmonic. So this is that. So once again here in this, when a station waves in a open organ pipe with two antinodes, one node, then length of the air column of the station wave L is equal to lambda by 2. Then wavelength is equal to 2L. Then from this one general equation, mu is equal to V by lambda. The lambda value is submitted, mu naught is equal to V by 2L. In a open organ pipe, first mu naught is on the fundamental frequency, first harmonic, and in second case, now I am selecting different nodes and different antennas. This is the open organ pipe. So now I am selecting this line. So now I am taking this line. So is there 1, 2, 3 antinode, node, because zero distance. So from this one, when your station waves traveling through the open organ pipe with the 1, 2, 3 antinodes and 2 nodes, then length of the air column. Now I am coming. This is the part. Means node and antinode. Lambda by 4. Node and node. Lambda by 2. And node and antinode. Lambda by 2. So total length L is equal to lambda by 4 plus lambda by 2 plus lambda by 4. Then total length L is equal to 2 lambda by 2. So now from the fundamental equation, what is that? Mu is equal to V by lambda. Here is lambda is equal to 2L by 2. Then in second one, I am taking mu1. Mu1 is equal to means second harmonic or first overtone. So mu1 is equal to V by lambda value to L by 2. Then mu1 is equal to 2V by 2L, and mu1 is equal to 2 of V by 2L, and then we can write mu1 is equal to 2 into V by 2L means fundamental frequency mu0. Means from the second equation, what is the conclusion? When a stationary waves in open argon pipe traveling with the 3 antinodes and 2 nodes at that time, the frequency of this one is equal to twice of the means 2 times of the fundamental frequency. So this is a relation. And third one is the third one. So third one is some different line. I am taking this third one. Different nodes and different antinodes. So now if you observe here 1, 2, 3, 4 antinode, antinode, antinode and antinode. Node means when a stationary waves traveling through the open argon pipes with 4 antinodes and 3 nodes. 4 antinodes and 3 nodes. Then length of the air column. Now I am coming to this. Node antinode, lambda by 2. Node to node, lambda by 2. Node to node, lambda by 2. Node to antinode, lambda by 2. So totally L is equal to lambda by 4 plus lambda by 2 plus lambda by 2 plus lambda by 4. Lambda by 4 is equal to lambda by 2. Lambda by 2, lambda by 2, lambda by 2. So L is equal to 3 lambda by 2. Means when a stationary waves traveling through the open argon pipe with the 4 antinodes and 3 nodes, then the length of the air column L is equal to 3 lambda by 2. Then wavelength lambda is equal to 2L by 3. So wavelength of the stationary waves in open argon pipe with 4 nodes, 4 antinodes, 2 nodes, then wavelength lambda is equal to 2L by 3. So now here it is 4 antinodes and 3 nodes. What is the wavelength? Lambda is equal to 2L by 3. Then frequency in this one, I am taking already I taken mu1. Now I am taking mu2 because this is the second overtone. Mu2 is equal to V by lambda value 2L by 3 to L by 3. Then mu2 is equal to 3V by 2L. Then finally how to write? Mu2 is equal to 3 of V by 2L. So V by 2L what is equal to? Fundamental frequency. Now I am writing it. Mu2 is equal to 3 mu naught. Mu2 is equal to 3 mu naught. Means when a stationary waves traveling through the open argon pipe with the 4 antinodes, 3 nodes, that frequency of stationary waves is equal to twice of the means 3 times of the fundamental frequency. So now here it is. mu2 is called second overtone and third means third harmonic. Just how to look like in a structure, see, same is like in a open argon pipe. Means left side suffix numerical number is overtone and right side multiple number is that one harmonic. So this from this one total conclusion. In a open argon pipe, the frequencies ratios mu0 is to mu1 is to mu2 is to mu3 dash mu n minus 1 is equal to how to look like 1 is to 2 is to 3 is to 4 is to dash up to n. So how to get that one? Stationary waves in a stature scene is the same as well. The stationary waves of the frequencies ratios is also same equal, but nodes and antinodes is different. In open argon pipe, in a stature scene, it will be totally different nodes and antinodes. As well as we can find the length of the air column, length of the stature scene based on nodes and antinodes. Just keep in mind that how many nodes and how many antinodes and how to find that one distance between node and antinode and node to node and antinode to antinode. Just we can find it this line. So this is that. Once again, here in this vibration modes in an open argon pipe. So now here it is. when a stationary wave traveling with the wave velocity v and frequency mu and wavelength lambda, then relation between these three quantities v is equal to mu lambda. Then from that one I need frequency only, mu is equal to v by lambda. So now I'm selecting one stationary wave one stationary wave traveling through the open organ pipe with two antinodes, one node. At that time, length of the air column L is equal to, this part is lambda by 4, this part is lambda. Why? The distance between node and antinode is lambda by 4, same in equal lambda by 4. So lambda by 4 is equal to lambda by 4. Then lambda value is equal to 2m. So that's lambda value and summating in this one. So in this one, first I am selecting, that's I am making fundamental frequency. So fundamental frequency mu naught is equal to v by 2m. So here this mu naught we are called fundamental frequency or first harmonic. And next one I am selecting the stationary waves. The stationary waves when they are traveling through the open organ pipe forming with the 1, 2, 3 antinodes and two nodes. Then when 3 antinodes and 2 nodes, then the length of the air column L is equal to 2 lambda by 2. Why? How is it possible? Node and antinode lambda by 4, node to node lambda by 2, node and antinode lambda by 4. So now lambda by 4 plus lambda by 2 plus lambda by 4 is equal to 2 lambda by 2. Then lambda value is L by 2. This value I am submitting in general equation. When that value is submitted in general equation, now I am taking that one first overtone in this one, second like that one, second node pipe. So mu1 is equal to v by lambda value 2L by 2. 2L by 2 I am submitting. Then we can get 2v by 2l. So don't cancel that one 2 by 2. Just because we have the one relation, just follow through the relation terms. So now mu1 is equal to 2v by 2l and mu1 is equal to 2 if you come on that one, v by 2l. Then v by 2l is equal to fundamental frequency. So now I am writing mu1 is equal to 2 into v by 2l is equal to mu0. Means when a stationary wave is traveling with the 3 antinodes and 2 nodes, that frequency is equal to twice of the fundamental frequency. And next one, when a stationary wave is traveling with the 4 antinodes and 3 nodes, at that time the length of the air column is 3 lambda by 2. How to get that one? Node and antinode lambda by 4, node to node lambda by 2, node to node lambda by 2, node to antinode is lambda by 2. So that is equal to the length of the air column 3 lambda by 2. When the antinodes is 4, 3 is the nodes. Then lambda is equal to 2L by 3 from the length of the air column. Then mu1 completed, means second overtone. Here is the first, mu1 is equal to first overtone or second harmonic. Next I am taking second overtone. When the second overtone if you selected, mu2 is equal to v by lambda value 2L by 3. 2L by 3 I am writing. So now mu2 is equal to 3v by 2L. So 3 of v by 2L. V by 2L is fundamental frequency. Now mu2 is equal to 3 mu naught. Here it is. If you are taking the second overtone, that is equal to the third harmonic. So the ratios of the frequencies in a open organ pipes, mu naught is to mu1 is to mu2 is to mu3 is to delta dash up to mu n minus 1 is equal to the ratios how to look like 1 is to 2 is to 3 is to 4 is to delta dash up to n. These are the vibration modes as well as frequencies ratios in a vibrations modes in open organ pipe. This is about our class. ఇంకెందుకు